I would like to welcome you to this workshop on combinatorial identities and their applications in statistical mechanics, which is part of the semester Combinatorics and Statistical Mechanics held here at the Newton Institute. We were supposed to be two organizers welcoming you this morning. Pierre Leroux from the LACIM, Department of Combinatorics at Université du Québec in Montreal, and myself. Unfortunately, less than a month ago, Pierre, who you can see on this picture at a better time, unfortunately, Pierre passed away. So many of you know Pierre much better than I do and would be able to speak more eloquently about him, about the man and his work. I will simply say that I have known Pierre since 2002. I first met him at the Séminaire Lotharingien de Combinatoire in Ellwangen. He was then interested in the Meyer expansion and its combinatorial aspects. I went to see him a few times in Orsay, where he was visiting shortly after, and we had very interesting discussions on this. He later kindly invited me to Montreal to speak at the Congress of ACFAS in 2004. 2 summers ago, we were contacted by Alan Sokol in order to organize this workshop, and we both felt honored by this responsibility and excited about the prospect of bringing together a community of people doing combinatorics and mathematical physics around such identities involving trees, forests, all kinds of combinatorial objects. This conference, I think, meant a lot to Pierre, and he has been involved in its organization almost until the last minute. I was privileged to learn the ropes of organizing such events with someone with his experience. He made plans to come here with his wife Madeleine for an extended period of time around this workshop, and he was excited at the prospect of this opportunity. However, on February 15, he phoned me, and usually we communicate by email, and his voice sounded weak. He told me that he was going to be hospitalized, and although he had much serious concerns facing him, he was feeling sorry that I was going to be alone, going to be on my own from now on. A week later, he was diagnosed with a cancer at an advanced stage, and on March the 9th, that was it, he was gone. So even from his hospital bed, his wife and his daughter sometime managed to bring him a laptop, and he would send me emails with recommendations about the organization of this workshop. In particular, I would like to point out that if you go on the program page and you go on the abstract for Gilbert's talk, which is the first talk you're going to listen to this morning, there is links to papers by Pierre Leroux on subjects he wanted, well, if he could, he would have talked about today. So I strongly urge you to have a look. I think I'll ask that an email be sent with the link so you don't have to fiddle around. The organizers of the semester, Peter Cameron, Bill Jackson, Alexander Scott, Alan Sokol, Dave Wagner, joined me in making this event an event which is dedicated to the memory of Pierre Leroux. So now I think I'll let Gilbert, who is a long-time friend and collaborator of Pierre, talk about him, and also he kindly accepted to give Pierre's the talk that Pierre was supposed to give on introductions to species. So,
thank you. First, I will speak about Pierre Leroux. Actually, I have known Pierre Leroux for more than 40 years, nearly 45, but more than 40, certainly. Pierre Leroux was the most complete man I have met in my life. Pierre was an excellent teacher and researcher. For example, he gave numerous courses on different mathematical domains. The students loved him. He gave numerous conferences around the world. He wrote about around 70 research papers in leading international journals or proceedings. He has been supervisor of dozens of master, PhD. For example, the last PhD student, Amel Kaouch, has not yet finished her PhD. She is there. She will speak this afternoon. She will have a poster session this afternoon. Pierre also was an excellent builder and rallying person. Rallying person means, as far as I can understand, he can bring people together. And he founded the research center LACIM, for example. LACIM is this, means Laboratoire de Combinatoire et d'Informatique Mathématiques. We call mathematical informatics. We don't say theoretical computer science. We say mathematical informatics at UQAM. UQAM means Université of Québec at Montreal, like University of something at San Francisco, I don't know, in San Diego. He created also, he was central in the creation of PhD program in combinatorics at UQAM. He created les Midis de la Recherche. These are conferences given at 12 o'clock in middle of the day to interest people to other subjects, many kinds of subjects in sciences. He organized or co-organized many international mathematical meetings, including this one, this present workshop. He has been president of the Canoe Camping Federation of the Province of Québec. You see, he's a complete person. He was also excellent administrator, vice dean for research at the Faculté des Sciences de l'UQAM. He was director of the Centre de Recherche LACIM, president of many committees, etc. Pierre also was an excellent explorer of nature. He was doing canoe camping exploration, making maps of rivers, even making maps of rivers which were not known. He was cross-country skiing, opening trails, things of this type. Pierre also was an excellent in helping people. He created a program for financial help to students. He was co-president of a financial campaign for the development of the university, which has disappeared. He even recently managed, this is a very interesting thing, he even recently managed to adapt his book on linear algebra to blind people. Reading like that the book, even the formulas. And he was also an excellent husband of Madeleine, an excellent father of Marie-Claude and Sophie. He was an excellent grandfather of Camille, Marie-Ève, and Philippe. Pierre was a very nice, simple, and friendly person. The world has lost a very important mathematician, and I have lost an excellent collaborator and friend. Okay. Now, I will speak. It is not actually the exact speech that Pierre was to give, because I cannot replace Pierre completely. But you see, I will speak about introduction to species and combinatorial equations. I have 60 slides, so that I will have to go rapidly. There is a dynamic connection between discrete mathematics and science in general, and it will greatly increase, not decrease, it will greatly increase during the coming decades. You see, we are in this, where is it? It's physics, we are related to this, but computer science, chemistry, physics, biology, mathematics, even human activity, public keys, method and encryption, etc. Now, you see, in analytical geometry, there is geometrical figures and formulas, and one can go, you see this and you see this, you know that it is the same, this is quite the same, this and this is quite the same. But in combinatorics, there is also analytical algebraic, algebraic combinatorics, combinatorial structures, and formulas, the same kind of things as above. When you see this, you don't write this, you write this. When you see this, there is no example. When you see this, you see this. When you see this, you see this. Now, I will start with an elementary introduction to species. Species is a kind of modern way to look at enumerative combinatorics or classifying combinatorics. Intuitively, in combinatorics, a structure S is a finite construction made on a finite set U. You do finite things on U, and you say, I have built a structure on U. U is called the underlying set of the structure, or U is equipped with the structure. The set alone has a structure on it. It is equipped with something. Or the structure is built on U, or the structure is labeled by the element of the set U. These are equivalent things to say. Okay? And first example, I will start with 25 examples, and then I will give 25 species of structure, and then give abstract definition, etc. First example, a tree on a set U, 27 symbols, for example. You see, this is a tree on the set of 27 symbols. If you don't put names, it will be called an unlabeled, but we start with labeled things. A rooted tree now is a tree with a special point, which can be anywhere, called the root. On the same set, this is a rooted tree. There is 27 more rooted trees than trees, because there are 27 ways to choose the root. An oriented cycle on U is a construction which makes you turning around in a certain direction. You see, there is n-1 factorial ways to put n points on a cycle. We can speak of even cycle or odd cycle, depending if there is an even number of points or odd number of points. This can be said also to any structure. A structure is even if the underlying set has even number of points and odd otherwise. There is a notion of, there is a kind of structure which is called a subset of a set. You see, you make the construction of choosing certain elements on the set. This is a subset structure on the set of how many points? Of 7 points. The set structure on a set means you do nothing. The construction is empty. There is only one set structure on any set. Only one way to put such a structure doing nothing. It can be an even set or odd set. A permutation on a set, which is not a list, not the same. A permutation on a set is a bijective, and it is a bijective undo function on the set. It decomposes in cycles. There are many permutations. There are n factorial permutations. An linear order on a set is a way to put the total order of the elements. N factorial ways, not the same. N factorial, not the same thing. The structure of partition on a set, you see, you cut the set into a set of non-empty subsets. Partition is a set of non-empty subsets. We'll see it again later. Undo function structure on a set is a way to put have a function on the set to itself. You see the image, this is a sagittal representation. The image of 19 is 55, the image of 55 is 18, and then it turns. This is, we can say these are rooted trees dancing around the dances. Set of rooted trees which are dancing, square dance, we can say. There is a bicolored polygon. This means you take a polygon non-oriented, it will come back later, and you alternately put colors, two colors on the sides. We'll see it later. A graph on U, and a connected graph on U. Okay. There can be graphs or connected graphs. Some degenerate structure. A singleton structure on a set, it can exist only if the set is a singleton. There is no singleton structure on the set of participants here because you are not singleton. There is singleton structure of the set of me, for example. And this letter, there is a singleton structure on this one if you consider it as a singleton set. There is a very degenerate structure. This is the empty set structure. It exists only on sets which are on the empty set. There is no empty structure on any other set. Okay, so that U must be non-empty. If U is non-empty, there is no structure. Involution structure, this image of this is this, image of this is this. You see an involution structure is made of fixed points and set of, I don't know what to call this, for exercises. But there are very much many more structures in this here, etc., etc. Now we will be more abstract. I started with examples. We start to be more abstract. You see, a generic structure on a set we can represent like that. The set and some line joining to a letter S means any structure on any set. A structure S on a set is said to be even or odd, as I said before, according to U contains an even or odd number of elements. Two structures, S and T, are said to be disjoint if their underlying sets are disjoint. These are useful terminology. Now, structure can be studied and classified by collecting them into species of structure. The definition of species of structure will come slowly. The interesting thing about species of structure is that you don't need to know what is a structure to know what is a species of structure. You will see. Before, come back to the examples, and I give a letter to represent the collection of all structures of a certain kind. For example, the end here, symbol end, means the class of all endo functions on all possible sets. See, there is a useful letter for each example that I gave. X is very important. It will come back later. X means the species of all possible singletons. You see, then we give a letter to a symbol to represent classes of structures that we just saw. Interesting one is the species of the empty set. There is only one empty set. The class of all the empty sets is made of one thing. We call it one. This is the ordinary one in mathematics, actually, because there is a structure 2, 3, 4, and the species, 2, 3, 4. But the most degenerate species is this empty species, more degenerate than the species of the empty set. The empty species, there is no structure on any set, even if the set is empty. Okay? This is the zero species. We don't know what is a species, but we start to understand what is. It is collection of structures, essentially. And the species F of all F structures. The species J of all J structure of all graph structure, for example. Where is J? Is it there? The graph of all graph. You see, this is a terminology. One must not confuse between the species and the structure. The species is the collection of structure, and the structures are the elements of the collection. And now we will see progressively what is a species. We can start to know intuitively. But before that, for example, for all the examples before, for any finite set U, we denote by F of brackets U the set of all structures of the kind F on U. This is a notation. See, this resembles to a function F of U. We put square bracket because this is a set here and this is a species here. Square bracket, not to be confused with some series which will come later, denotes the set of all structure of a certain kind F on the set U. We'll come for the definition slowly. For example, if F is C, the species of cycles, of oriental cycle, this is a C structure. This is a special instance of the class of cycles. And if U, there is one thing which is, for example, this example, if U is a set, then C of the set, F of the set, means the set of all structures of the kind C here, which can be put on the set. This is a set. Each element is a structure. There is 6 possibilities of cycle structures on a set of 4 elements. This is trivial first, but it will be less trivial as when we will come. Now, there are 2 important properties of these examples that we saw before. It is that, first property, we look for cycles first. For any finite set, there is a finite set of cycles on it. It is very trivial. For any, this is less trivial, which will be important later. Every time you have 2 sets and a bijection between the 2 sets, for example, MNPQ, ABCD, suppose you have a bijection, this bijection, then it carries over the set of structures on U and on V. Automatically, there is a renaming arrow, which we call C of the bijection. Those who know category theory will realize that this is a functor. Any cycle on U, that is any element of C of U, is carried by renaming the underlying element by the bijection, is carried to a corresponding one in the other set. Okay? This, we can say, this bijection, C of beta, relabels via the first bijection each cycle on U to a corresponding cycle on V. These 2 things are the abstract things that we need to define a species of structure. Instead of writing C, we will write F. And, oh yes, a third one is the renaming of elements of U to elements of V, and renaming elements of V to elements of W amounts to renaming via the composite bijection. But if you look at the cycle, there is a coherent transformation. 2 successive transportation of structures, we can say, amounts to a single one along the composite bijection. This is functorial property. And we come now to the abstract definition of Joyal in 1979. A combinatorial species is a rule, F. F is a rule, or computer program, anything you like, is a rule which do 2 things. It generates for each finite set U a finite set F of U. It generates the rule for each bijection between 2 finite sets, another bijection called a rule of beta in a coherent way. If you compose like that, it is the same as doing that. And you see, to define a species, we don't need to have structures. We need to have a rule which does that and that, and in a coherent way. And any element of F of U, because you see, F of U is a set by definition. For each finite set U, we have another set F of U. Each element of F of U is called an F structure on U. You don't need any axiom. You say an element of F of U is called an F structure on U. An element of C of U, if you take the examples of cycles, will be a C structure on U or a cycle. And now any bijection, it turns out that this is a bijection automatically in the definition, but we don't need actually this. This it should appear. Okay. This implies that this is a bijection. But in any case, the bijection F of beta between structures on U and structures on B is called F relabeling via beta. Now, a way to represent, you see, this is a way to represent a structure F, S, F structure S on U. The structure, the kind of construction F and U. This is a notation, graphical way to represent any structure of kind F on U, or you can write it like that if you don't mind to, if you don't like to put names, and you can put a big F on the set. This, for example, if this is capital C, this will be a cycle, generic cycle on the set. Now, counting structures of a given species, we do that now. The properties of relabeling, transportation of structures that we saw before, implies that the number of F structure on a set depends only on the number of elements of the set. That is, the cardinality of the set of F structure on U depends only on the cardinality of U. This is very trivial. Now, because of that, we can, for counting purposes, take U to be the set of n standard set 1 to n. I put underline n here not to have too many brackets, because normally if you could put square bracket here, it means 1, 2 to the n, but there is already a square bracket in the notation. You see, now this is the generating series of a species. The series is not the species. The species is not the structures. Species is the class of structure. Generating series is a counting algebraic device to count structures. So that Fn is the cardinality of the set of all structures on n. That is the number of F structures labeled by 1 to n. And there is a generating series with round parentheses, very important. Round parentheses and small variable means the series defined by that, whose coefficients is the number of structure on n set, and there is a factorial here. This is the generating series of the species by definition. And we'll see that generating series leads to a connection between combinatorics and analysis. Euler knew that. With the theory of species, it becomes more a science than an art. You will see that we'll see. F of x is, by definition, this series. For example, if you take, now I start with few examples, and then there will be chemistry of species. We combine species, and then it will be more and more complicated. You see, for the species S of permutations, the series, you put the number of permutations, which is well known to be n factorial, divided by, always by a factorial in the general definition. This is the geometric series. As soon as you see the species of permutation, there is this automatically geometric series underlying that. But this is only algebraic aspect. This doesn't see the cycles turning. This is very degenerate thing. The species is more combinatorial. We'll see later. P, the species of subset. P of x, the coefficient, there is 2 to the n subset of an n set. Because of the factorial, it gives e to the 2x. This seems to be complicated, but we will see later with the combination of species that this is very trivial. You can see it in many ways. E, the species of set, because in French, E is ensemble. The first letter of ensemble is E, and it turns out the series of sets is the exponential. We are very lucky. Capital E gives the small e. And Euler would be very happy also, because capital E gives small e. You see, because there is only one set structure on each set, you do nothing. So that the coefficient in front is 1. Now, the species of even set, you see, if you have 3 element set, there is no even set on it, 0 coefficient. Coefficients are 1 if and only if. The coefficient is 1 if and only if the set is even, and 0 otherwise, cosine, hyperbolic cosine. Species about set, hyperbolic sign, very trivial. Now, species of list, linear orders. We know that n factorial way to put the total order and then set, still the same series. Not the same species, but the same series. And we'll see later why it is not the same species. We saw it is not the same species as permutations because we saw the graphic which was different, but there is deeper things why it is not the same species. The species of cycles, this one for this one, up to now, one must know that there is n minus 1 factorial, and that one must know that the Taylor series of this is a Taylor series of log of 1 over 1 minus x. If one knows in advance Taylor series, but we'll see later, this is very trivial from the species point of view. We'll see this identity in 2 or 3 different ways. This way is because one is knows that it is log, but we'll see one does not need to know that this is log to know this later. The species of even cycles, you put only a coefficient n minus 1 factorial only if n is even. It gives this. Species of undo function, this is this series. You see in theory species, the series doesn't need to converge. The radius of convergence of this is 0. It converges only if x is 0. No, 1 over e. I made a mistake. 1 over e. I saw that you were 1 over e. But this one, you see, doesn't converge because this is too big. It converges only if x is 0. These are formal series. Now, the species x of singleton, why did we write capital X a few transparencies before? Why did we write capital X for the species of singleton? It is because if you take the power series associated with that kind of species, there is a coefficient 1 if and only if the cardinality of the set is 1. 0 otherwise, this is small x. So that the series of capital X is small x. Okay. Now, we can combine series to give new series. Actually, we can combine series to give an infinite number of series. But here are the most important 4 combination of series. You see, you can add 2 series to have a third one. At the level of coefficients, it's very easy. You can multiply 2 series to have a third one. The coefficients are a little more complicated. You can substitute a series into another one if the substituted series has a 0 constant term. This is a little more complicated. Fadi-Bruno formula hidden in that to have the coefficient of the resulting. One thing is very interesting. You can differentiate a series simply by shifting the coefficient. You see, if I differentiate this, I put the n in front, it becomes n minus 1, and I rename the index n minus 1 n minus 1 here, n fn, n. You divide the n with the n, you shift, you get this. Very trivial. So that differentiating, differential calculus on series means shifting on the coefficient. And this table suggests the following combinatorial operation on species. These are the operation on structures, but on species. This is the way to define new species in terms of all species. There is an infinite number of ways. These are the first, more important. You can add 2 species to give another species. What are the structures belonging to the new species? The structures are either a structure belonging to the first or to the second with, if you take disjoint, if there is structure in common, you color them in 2 different ways to make it additive. The product of 2 species is another species, not a series, another species which is called f times j. A structure on, for example, this 6 element set, a structure, f times g structure, is obtained as follows. You cut the set into 2 disjoint subsets, possibly empty. You put on the first subset a f structure and on the second subset a j structure, and you call this a f times j structure. If you take the collection, this is the species of this species f times j. You see, it is another pair of a f structure and j structure disjoint. Now, substitution is very interesting. F composed with j structure is a f structure built on j structure, f of j, very trivial. You put F structure on J structures which are disjoint. You call it a F composed with J structure, and at the level of species, you write this equation. One needs to be, there is no structure on the empty set of the kind J. In order, if you accept structures of species J on the empty set, then you will have an infinite thing, an infinite possibility. Now the species F prime, the derivative of a species is another species. That is, the derivative of a class of structure is another class of structure. A typical element, a F prime structure on a set, is a F structure on the augmented set by extra element. You see, suppose you have 4 elements, A, B, C, D. You want to put a F prime structure. You have to add first an extra element and take the 5 elements now that you have, and you put the F structure on it. This is called a F prime structure on the old set. This extra element is not in the underlying set of the F prime structure. It is a part of the structure itself. We'll see many examples.
And it's not a distinguished element.
It is not a distinguished. This element is extra. You will see. Sometimes we can put in the rooted tree, for example, we can distinguish an element as the root, but this one is not, will not be F prime, the rooted. The element must be extra. We will come back to it later. Now I will give some examples. Oh yeah, before, you see the operation on species were made in order that these equations are true at the level of series. You see, if you compose 2 species, you have a species of F of J structures. You take the series of this, it gives exactly the composition of the series F, and you put in it the series of J, substitution. The species F prime amounts to differentiate if you take the series. Now we come with examples which will be very easy to understand. For example, the species of set is the sum of the 2 species, because any set is either even or odd. So that it turns out that for the series you have automatically that. So that we have this. If we know that the series of even is this and this, it gives this identity, well-known identity, but it turns out to be a consequence of this. Very trivial. I start with trivial. Now, the species of derangement. What is a derangement? A derangement is a permutation without fixed point. Okay? I say that species of permutation is the species of sets times the species of derangement. Why? Because if you take an instance of a permutation, this is dancing points into circle. There are some dancers which dance with themselves, and you put them aside. This is a set. And the complement of the set, you make a derangement. A derangement is a permutation without fixed point. So that S is E times D. So that automatically, because of this, automatically the series of permutation is the series of sets times the series of derangement. Whoop. This, I don't know how to set. Now, so that, but we know this very trivial. It was 1 over 1 minus x. E of x, we knew it was e to the x. So that we can isolate d of x. D of x is e to the minus x times 1 over 1 minus x, because you can put this side. So that if you manipulate the series, take out the coefficient, you have for free the number of derangements, which is well known in probability theory. Number of derangement of an n set is n factorial times the alternating sum of the first up to n element of the exponential series. But this is only a consequence of this. This is perhaps the simplest way to prove this formula. Now, the species of endo function is the species of sets into which you put the species of arborescence, that means rooted tree. A is arborescence in French, means rooted tree. Why? Because suppose you take any instance of an endo function, you see dancing rooted trees in 2 cycles. So that it is a permutation of rooted trees. It's very easy. Permutation of rooted trees are endo functions. And so that at the level of series, you have automatically the series of undo function, which we knew it was that, is the series of permutations into which you put the series of rooted trees. Suppose you don't know what is the series of rooted tree. We know that this is the series of undo function because each element has n to the n undo function. The series of permutation is 1 over 1 minus x, but you substitute ax in 1 over 1 minus x, and so that you have this curious identity. If you want to count this is not the easiest way to count undo functions, but it is known that the coefficient for, not undo function, but for rooted trees, it is known that the coefficients are n to the n minus 1. We know in advance, but suppose we know nothing. It gives automatically the series of rooted trees is the quotient of these two series. This one starts with 1, this one starts to 0. And suppose we know that it is n to the power n minus 1, the coefficient. It is difficult to prove this identity analytically. It is free from this. It is gratis. Now, the species of permutation is the series of sets into which you put the cycles, oriented cycle. Why? Because any permutation is a set of cycles, and this means of, the literal means of. So that for free, the series of permutation is the series of sets into which you put the series of cycles. This one we knew, suppose we knew. The for sets we knew it was exponential, so that 1 over 1 minus x is e to the power c of x. Suppose we don't know c of x, we take log both sides, and we get the formula we saw before when we knew what was the Taylor series of a certain series. But one here doesn't mean anything to have this conclusion. Now I will go rapidly on this. For Stirling numbers, you see, the species of permutations having exactly k cycles, and the species of sets of k sets. Permutations having k cycles are k sets of cycles, and everything is free. You see Dubinsky, no, not Dubinsky. We'll see Dubinsky later, perhaps. But this is one of the formulas for Stirling number of the first kind, which is only a consequence of this. Now, species B of partitions, of set partition. Partitions are sets of non-empty sets. E plus means the species of non-empty sets. So that the series, and the series of non-empty sets is very easy. Series of sets, you subtract the constant term. So that for free, the series, not the species, this was a species, the series of partitions is the series of sets into which you put the series of non-empty sets. It gives e to the x minus 1, because series of sets is e to the something. So that for free, and you can put 1 over e. For free, you get the Dubinsky formula. You take only the coefficient in this, you will get this formula. This formula, actually, at the beginning, Bell, when he proved this formula, it was very complicated. It is for free. This formula is simply a reflection, algebraic reflection of the fact that partitions are sets of non-empty sets. Same kind of thing to have partitions on having k class, which is related to Stirling number of the second kind. Now, the species of subset I called before P. Okay, P. What is a subset? This is a subset. It shows a certain elements of the set. A subset is a set together with its complement, so that it is a set together with its disjoint set, so that it is the square set times set, so that the series of subsets is the square of the series of sets. It is the square of e to the x. You see, it gives another way to see that there is 2 to the n subset, but complicated way, but everything is coherent. For example, here the species of permutation having only even cycle. You can combine any way you want, so multiple substitution any way you want. It is, you see, permutation having only even cycles, these kind of structure are sets of permutations having of even size. And it gave this, if you look at it in detail. Now we come to differential calculus. You see, I will show that L prime, the derivative of the species of list, is the square of list. It becomes more differential calculus. Why? Because I said before that to obtain a F prime structure on a set, for example, this set, 1, 2, 3, 4, 5, how many? 6 points. To have a L prime structure on a set of 6 points, you have to add an extra point, and you put a L structure on it. But if you look carefully, the extra point will be in some place in the snake, but the underlying set are only the 6 point of the L prime structure. So that if you had this, you have this, two lists, a first and a second. If you have the right-hand side, you have also the left, because you put an extra point and you continue and do that. These are the same kind of things. So that the derivative of the series of lists must be the square of the series of lists. And if you look carefully, it will be coherent with this formula. If you take the derivative on 1 over 1 minus 6, there was some minus signs which will combine. It is well known. But the real reason why is this true, it is this. Combinatorial.
So in the L prime structure, or in an F prime structure in general, the extra point is distinguished.
Is distinguished, but outside.
Yeah, it's outside, but the
we'll
F
come
prime
back to the
structure
point.
you have the extra. The structure includes the F structure on
yes,
the extra
the,
set
the,
and
the structure,
picking out a point.
Okay, in okay.
I guess it is the same as rooting.
Okay, in any case, okay. On the extra, you must put a F. On the augmented set, you must put a F. But it is called the F prime on the original set.
But what I'm saying is the F prime structure is not just the F structure on the augmented set. It also point out
yes,
which
yes, you
is
must
the
remember
new
which this extra point. You must remember it is extra point. You must remember. One way to define an extra point is very interesting from set theory. Sometimes the augmented set of a set is the set union singleton of the set. So you take a photograph. Suppose I want to add an extra point to you. I take a photograph of this. Oh, very good. Suppose I want to make an extra point on the set of participants. I take a photograph of the set. I put as an extra element. And this is a canonical way to write an extra point, to find an extra point. So that this point can be canonically interpreted as the photograph of all the 6 previous, 7? I thought it was 7. A photograph of these 7 is this extra point, to be technical. Okay, very interesting here. The derivative of the species of oriented cycles is the species of lists. It becomes poetic. Why? Because suppose I have 1, 2, 3, 4, 5 points, and I want to put a C prime structure. What do? I take a photograph of the 5 points, and I call it an extra point, star point. I put a C structure on the augmented set. It gives the same information as putting in a list the original points. If you put in a list the original point, you can add an extra point to make a cycle. So that C prime is L. For free, you know that derivative of cycles is list. So that the series of cycles must be the integral of series of lists. But the series of lists, we know it is 1 over 1 minus x. So that the series of cycles is this integral, this is this. A third way to find the series of cycles is because of this. Now, very interesting. The derivative of species of bicolored cycles is the same as the species of odd lists. Why? And it is the same as the species of derivative of even cycle. Very interesting. You see, suppose I want to build a p big prime structure on a set of 1, 2, 3, 4, 5 elements. I add one element extra. I put a p big bicolored cycle on it. It gives this. But there is a canonical way, you see, to make a list with this. You see, I start with the red. So suppose I say color red comes first. I start with the red, and then it becomes arrows. And if I have this, I can rebuild this by going backward. But for the species of even permutations, if I differentiate it, what do I do to do that? I put an extra point and I put an even cycle on the augmented set, which is 6 points. It is possible to put an even cycle. So that this is the same thing as this. So that the derivative of the species p big bicolored cycles is the same as the derivative of even cycles, but these are not the same species. There is not the same automorphism group, because one consequence to be same species is you have the same automorphism group. These two are not the same, but they have same derivative. So that in the theory of species, you may have same derivative, but not differing by a constant. In the level of series, these series differ by a constant. Maybe the constant is 0, the series of this, but they are not the same species. This is very interesting. Here, the derivative of partition species is the set species multiplied by partition species. Very easy to see. You augment the set to an extra point, and you put a partition on the augmented set. The extra point is in some of the sets of the partition, so that there is a distinguished set which comes from the augmented set of the partition. So that you see a set, this is an E structure, together with a disjoint partition, which is a B structure. So that if you take the series, you have for free this recurrence, very well known recurrence for the number of partition on n plus 1 set, connecting with the number of partition up to n element set. Now there's some implicit definition also. Species of rooted trees is species of singletons times the species of sets of rooted trees. Very easy. Any rooted tree is a singleton and together with a set of rooted tree. So that you have for free for the series, you can solve with Lagrange inversion, or otherwise you find this automatically from this equation. You can go backward, you can do many things. This is only one example. Species of vertebrates. Vertebrate is a pointed rooted tree. A rooted tree, you see, suppose this is the root, this is a rooted tree, but if you point it, which is if you point an extra point, you have a vertebrate. André Joyal was, when he invented the species of vertebrate, he was in Australia and he was seeing lizards. I will call it vertebrate, this kind of thing. You see, this is the head, the tail. I don't know which is the head, what is the tail, but you see, if you see a vertebrate, you see a list of rooted trees because you go along the spinal column, something like that, and you see rooted trees in the list. So that the series of vertebrates is the series of lists into which you put the series of rooted trees. But the list of rooted trees are same as permutation. No, the list of rooted trees, okay, the series is this, but this is the series Amando function, not too difficult to see. So that if you count things, there is n vertebrate because there are n ways to put to point a vertebrate. An is the number of rooted trees. Vertebrates is the same as Amando function. This is n to the n. So that n to the n is n times an. So that an, to obtain the number of rooted trees, you simply have to divide by n. You have n is n to the n minus 1. This is one of the proof of Joyal of the Cayley formula. So that Cayley formula is a consequence of vertebrates are lists of rooted trees. Now, poetic things. The derivative of the species of trees is the species of forests of rooted trees. Very poetic. The derivative of the species of trees is the species of forests of rooted trees. Why? Because if you have a set of black points, you make a tree on the augmented set. This is a tree. No special element chosen, but we see one special for free, but there is no special as being a tree on the augmented set. And this information is the same as this, because this extra point is joined to trees, which gives roots, so that this is a set of rooted tree. This is a tree on an augmented set, so that the derivative of trees is forests of rooted trees, but that means sets of rooted trees. And you have automatically for series the identity like that, and so that this is known to be the number of the trees. I mean, derivative of trees is forest, so that you have for free. The number of forests is n plus 1 to the n minus 1. This is easy also. Graphs are sets of connected graphs, so that the series of graphs are exponential series, very well known, of the series of connected graphs, so that the series of connected graphs is the log of the series of graphs, so that you can very easily obtain a recursive formula for connected graph by going to indeterminate coefficients. Here, interesting also, the species of ballots. What is actually, this is a species of results of a ballot. Suppose you have a ballot, 4 are elected as president, for example, 4 are ex equal, 3 are ex equal second, 1, 2. You see, the result of a ballot is a list of non-empty sets. So that ballots are lists of non-empty sets, so that the series of ballots is the series of lists into which you put the series of non-empty sets. Non-empty set, we know it is e to the x minus 1, so that list into which you put this series gives this series of ballots, and you make some manipulation, you find this. This is always an integer. You find this for free by collecting the nth coefficient of this series. This is quite difficult to prove directly.
So maybe
I don't know which person proved it first. No. Involutions, for example, involutions are sets of singleton of this.
Gilbert question. These non-empty sets, they correspond to what?
To e to the x minus 1.
No, I'm not.
Okay. Yeah.
These are the number of votes for a candidate, or?
No, I understand.
These non-empty sets, I mean, in the ballot.
Oh, yes, because you see, suppose this one is empty, we can say this is, you can drop it and put an arrow. So you take non-empty sets because you take the winnings together, and then the seconds together. If there is no third, you put the fourth as the third. So that you need to have non-empty sets in each level, because if there is an empty set, you don't count it. Yes?
For this one, instead of ballots, you can say that it's surjections.
Maybe something like that. There may be some equivalent weight. I call it ballot because it is funny.
It's a pre-order, I guess.
Pre-order. Pre-total order. Pre-total.
Ordered partition.
Ordered partition, something like that. Okay. Now, this is, you see, the species of involution is the species of sets into which you put singletons or pairs of elements. E2 is the species of 2-element sets. And you have for free this. Now, you see classical formula for calculus, for example. Derivative of a composite is the substituted into which you put the derivative of the substituting, I don't know, times the derivative chain rule. This is very easy. You see, suppose you want to put, you want to describe a F composed with J prime structure on a set of black points. You augment the set with one extra point. And on the augmented set, you take a F composed with J structure. And now, the one J structure which was containing the augmented, you can put it together aside, give the G prime. And the others, you can put a star instead of this G to remember where it was glued. And you have a F prime of G's. This is a F prime of G's. because F prime is a structure, F prime structure, you have to put an extra point. This is the extra point. And on the real points, you put G's, G's, G's. So this is F prime of G structure times a G prime. So that this is coherent with the classical chain rule.
I'm sorry, does that,
Okay.
that picture seems to require that on a single element set there is one G structure?
Interesting thing. Okay, very interesting. Maybe we'll talk before after. Okay, maybe there is some restriction on this.
This is,
I'm not sure.
you should point out, this is now a formula of the species level. This is not just the
This is a formula for species, not. You see, this is automatically for differential of series automatically. This is species. But for this singleton, perhaps we will speak after. Because I want to go, I have up to 11, I think. So maybe I will be very rapid, okay. More advanced theory, now will be rapid. More advanced theory, because it encompasses polya theory. It has many things in the theory of species. You see, I recall species abstractly. Given bijection, we have another bijection coherent. This is, I recall the definition of species. F structure is an element of F of U. If you rename the elements, you rename the structures along bijection. Now, S is a structure on a set of species. F of U is the same as S belongs to F of U, is the same as to say S is an F structure on U. Now, suppose you transport a structure on the same set. No, this is, what is it the same set? No. It is. Okay, isomorphism. Two structures are said to be isomorph if one is transported into the other by renaming their elements. Very trivial in algebra. You see, if you have a species, you have automatically the notion of automorphism of structures, because an automorphism of structure is a bijection of the underlying element set into itself, which makes the structure equal after renaming the elements. So that if you have a species, you have the notion of automorphisms of any structure in the species. You can weight species also. Instead of taking sets of structures, you can take weighted sets, and you can put a weight on the structure. This is the notion of weighted species. Everything carries very well. For example, suppose you take the species of graphs, you can weight the graph by alpha to the number. Alpha will be what? The number of arrows, edge, I don't know, arcs, edge, edges, 5 edges, no, little mix, what is this? Little mix. But you see, it is written. Alpha to the number of edge times beta to the number of two connected components, for example. This is a statistics on structure. Interesting thing is that if you transport along bijection structures with wakes, the wakes are invariant. If the wakes are invariant, you call it a weighted species. Okay? And you can label or unlabel. You see, labeled rooted tree, unlabeled rooted tree. What is an unlabeled structure? Is an isomorphism class of structures. Isomorphism is a part of the concept of species, so that unlabeled are parts in the information of a species. You have the information of unlabeled things. You have also the information on asymmetric structure. Asymmetric structure is a structure whose automorphism group is trivial. You see, this is an asymmetric rooted tree. If you rename the elements, the tree will always change unless this is the identity renaming. Asymmetric structure means that you have only automorphism group or identity. You can unlabel a symmetric structure. Now, polya theory can count things which are unlabeled, species also. We have 3 main series. We saw first the counting series of labeled structures with factorial, but there are 2 other series, in fact, infinite number of series. The first, most important are these 3. Here, there is no factorial. You put a tilde on the name and on the name of the species. The series corresponding is a number of total weight. This is weighted. Unlabeled structure. Unlabeled asymmetric, you put a bar on it. Now, For example, for rooted trees, you see the tree series, there are less unlabeled than labeled. Labeled, there are 9 on 3-element set. Unlabeled, there are only 2. And asymmetric unlabeled, only 1. You see, but in theory of species, we can compute all these series with certain tools. You see, before I go further, there is two kind of equation between species. There is equipotence of two species, means that for any set U, the number there is a bijection between the F structures on U and the J structure on U. This is called equipotence of species. For example, there is as many permutations on a set than lists. When you have equipotence, you have only equality of the first series, but you don't have equality for the second and the third series if you need only equipotence. Combinatorial equation will be stronger than equipotence, which will allow to have not if and only if, but arrows from left to right. For example, here, this is the simplest example. Suppose you take the species of permutations and lists. They have the same labeled contained series, the geometric one. But if you use Euler formula, for example, you will see that unlabeled permutations are as numerous as partitions of integers. It gives this series. But the unlabeled list, there is only one unlabeled list on n nodes. You put a list on n node. So that, you see, the series are not the same. This is much more complicated than this. So that this implication is not true. For asymmetric, also this is not true, the implication. But now we need a combinatorial equality to have good implication. Combinatorial equality means for any set U, there is not only as many structures kind F as of kind J, but it must be coherent with the renaming of elements. Suppose you take a F structure and U, you rename it along a bijection to give F structure on V, and then you transform it along this bijection on a J structure on V. It must be the same thing as going this way. This is combinatorial equality between species. This is stronger than equipotence, and we write it like that, and we even write equality in our combinatorial book. And with this kind of equality, which is natural bijection in category theory, we have this implies all these three. You see, we write this instead of it, and we call it combinatorial equality. I will go very rapidly. I recall the sum, product, composition, and derivative. Okay, pointing. Now, pointing is F point structure is a F structure into which you have pointed an element. It is the same as taking a F prime and put the pointed element aside. So that this is a combinatorial equation. The pointed F structures are the singletons multiplied by the derivative. See, this is a combinatorial. So that pointing is x times ddx. It is n fn. It comes from simply this drawing. You can do much more complicated thing. Here, okay. I recall that the series are not the same. The series are not, the first series when you multiply or substitute goes correctly. But the other series, tildes, doesn't behave correctly, and bars also contain unlabeled, and unlabeled asymmetric doesn't amount to do the corresponding thing on the series. So that to restore, we need two new series with an infinite number of variables. To each species F, we have a series with an infinite number of variables, which is a collection of infinite number of polynomials. Robinson, Joyal created these things. Joyal created it in the context of species. The interesting thing about this, I will not go into detail, is that it makes generating, the power of generating functions into into Polya theory, because this is a series of polynomial, Polya polynomial. I created the context of species, a symmetry index series, which is a kind of series like Polya, which count unlabeled asymmetric things. And these series behave well in front of all the important operations on species. Okay? And then there is some, for the composition of two series, we have this in Polya theory. Don't go into detail. But this series Z and gamma encompasses all the old series in one variable by such a specialization. And there is, as a corollary, you can compute unlabeled f of G structures in terms of the ZF and ZJ. So that there is one principle. Every combinatorial equation characterizing a species gives rise, using these, for example, operation, gives rise to 5 corresponding equations characterizing the underlying series. And in fact, there is infinite supply of other operations and series. This is only the 5 most important series on a species. I will go rapidly on this. This is, you need to put label, you need to put weights and to define these two series. In any case, it will be available. Okay, I'm ending. Okay, I'm ending. You see, these are atomic species. These species are irreducible under sum and product. Every species is a power series in these things. Okay, molecular decomposition. You see, integers is part of series in X, is part of virtual species. These are species which we can subtract. You see, this equation gives rise to 5 equations. This is Leroux, Arthur Robinson, Leroux asymmetry formula. This is the dissymmetry formula of Leroux, Lagrange inversion. You can put weight on structures, and it weights the connected components. You see, just to show you some formula, not trivial things. You see, these are Mobius function and this. These are very curious things. Now, the species, you see, you take a class of blocks, two connected graphs, and you take the connected graphs whose blocks are in this class. This drawing is supposed to prove this formula, and you have 3 for the series. This is characterizing. You point to the structures, and it characterizes the unpointed one. This is Pierre Leroux formula, the symmetry theorem. But if you want to know more, it is in this book. This book is in my lecture. No, it is in the program. You can click and
the abstract,
it is in the abstract
for this lecture.
Yes, everything is in this book. And I wanted to finish with Pierre. Thank you, Pierre. You see, this is the real Pierre who was giving a lecture, and in his lecture at the end he had 2 photographs of him like that. And actually, this is not myself. I was there. I was helping Pierre Leroux. And okay, and I put with Photoshop a face of mine. Merci, Pierre. Thank you.
Is it true that if some spaces are related by means of this operation f prime,
Yes.
then you can differentiate the generated function?
Yes.
Yes.
You can differentiate. Yeah. If you take the generating function of the derivative of a species, it will be the derivative of the generating function. And you can put successive derivative, you can put many variables, partial derivative. We did not speak about species of many variables. And the funny thing is that you can also, the operator xd, dx, you can iterate it. And I have found recently with one of my students a way to generalize the on a two variable species f of x1, I can put, instead of elements of kind y, I can put the operator of derivative with respect to x. Suppose you take the species x times y, it gives x ddx. See, this is a general pointing operator I've created recently. Is it in China? Yes, in China last summer we presented this. This is very interesting in some sense, I think, because it generalizes the operator dx dd, generalize this, which is, I don't know, creation, annihilation operator. I don't know, I'm not a physicist. Creation x, annihilation ddx, something like that. So that it is a kind, you see, f can be cycles of two kinds of points. For example, suppose this is f, cycles of 2 points, x points and y points. I can replace y by ddx. I can replace y by ddx, and this thing acts on species. You can differentiate in structural way species to obtain new species. I don't know what it means, but perhaps physicists will know what it means. I don't know. You generalize this operator. I'm not sure if I answer your question. Yes?
With species, can you give a combinatorial meaning to the Laplace transform?
Pierre Leroux has done, perhaps with Xavier, we can give, but it is not in the context of, you see, in the theory of species, there are many integrals of a species which does not differ by a constant, many integrals. And the Laplace transform is one integral. But if you work on linear species, Pierre Leroux has worked very much on that. Linear species are species whose structures are built on already linear sets. Sets are already equipped with a linear order, and you can do Laplace transforms in this. But for general species, Laplace transform is not well adapted. Perhaps we will have to study more the integral calculus with the multitude of integrals. But I don't know how to do that Laplace transform for general species.
Well, let's thank the speaker again.